later session, so if you have questions, we can go a bit deeper into some topics, and so explore some technologies a bit more if you want. So we can do this quite interactively. So just one slide about myself. I work for SES Engineering. I'm senior manager there on system architecture and innovation. So I work on new satellite systems, currently in SES 17 and O3b mPOWER, NEO constellation, and we're in the process of designing the next generation for SES satellite data communications. So I personally responsible for the dynamic resource management of those systems, so the software that dynamically allocates capacity on those systems. What did I do? So I graduated from the University of Karlsruhe in Grenoble Institute of Technology in electrical engineering and information technology with a double-inch degree, master's degree. And then I did my PhD with Professor Björn Ottersten, that maybe you know. He's heading the SMT. Then I worked at SES. Before my PhD, I worked at SES, and then I interrupted my work, and then I worked again at SES, and then at NewTek. At NewTek in Belgium, I designed and worked on modems, so on implementing modems, FPGAs, and real-time systems for satellite modems. And then now I'm back at SES doing exactly that. Okay. So the talk is intended to be about ground segment aspects of modern satellite systems, a bit give an overview of what is happening on the ground. So what are we actually trying to accomplish with communication satellites? What are the applications, broadcast, data communications, and what technology do we find on the ground segment, on the gateway side and on the terminal side? And I dig a bit into different interesting aspects of the ground segment technology. And in such a talk, obviously, I cannot go into every single detail, so if you find something interesting, just let me know, or if you want to dig a bit further, let me know. I also want to talk about system concepts, so I give the example of SES systems and how our satellite constellation is built, and then talk a bit about these aspects. So the SES fleet, I wanted to give this overview because that shows a bit what we're doing today in terms of operations and what type of applications we are running today and what we're currently building. And that actually relates then also to the topic of current and future ground segment technologies nicely. So you have here just an overview of this SES satellite fleet, all the geostationary satellites around the world, and currently the new ones are in red. It's a bit old, so that one is already in orbit, and we're currently building SES 17. It will be here, somewhere at 67 degrees west. And then the O3b mPOWER constellation, which is a NEO constellation at 8,062 kilometers. And that constellation is replacing the current O3b constellation, which is the NEO constellation already in operations today. So that's the current overview. We have ground segment space stations, so gateways around the world to operate these satellites. The main ones is here in Bedstov, and then we have an important site also in Manassas in the US for the satellites there, and several other sites in the US, and then in Asia for the satellites over that region. Those are interconnected via fiber ground infrastructure, and this is the way we operate our satellites today. And you will learn throughout the lecture what actually changes with high throughput satellites. High throughput satellites are the type of satellites we currently have put in operation, so it's SES 12, 14 and 15, but much more SES 17. I'll explain a bit more about what makes this satellite so unique a bit, and O3b mPOWER also it's a bit different. So satellite services. I just want to give an overview of what are we actually selling, what are the services we're selling. SES became very popular through broadcasting, so TV broadcasting. It's a very traditional satellite application, but it's also one that is actually commercially very viable. So compared to many other applications, it's one that does have a real commercial impact. And SES has been broadcasting in Europe, and you probably know that Astra has been a satellite system since many years in Germany, France, and the UK. Spectrum on Astra, and that through acquisition it became a company that is now operating worldwide, and we are currently living really a transition towards a much bigger focus on data communication. So broadcast is seen as being the current very important application, and data communication becomes much more important now, and everybody recognizes data services, internet access, and different types of data services as the next step. And actually, what are these data services then composed of, which are coming next? So there are different applications for satellite data communications. The first one is in the industry called IP trunking. And IP trunking is the interconnection of big data infrastructure on the ground of a remote place towards a backbone. And that's, for example, the case where you have areas which are badly connected by fiber, and they need to be interconnected to a backbone, and there's no other way, and then the satellite uses its possibility to have good coverage to provide this infrastructure. That normally happens with very big antennas on both sides and professional equipment on the ground, big data rates. Typically those are several hundred megabit today. And for example, SES is selling that in the Pacific, to Pacific Islands, Papua New Guinea. Some islands, they don't have fiber, so they use satellite for that connectivity, but then they have very big antennas on the island, and the data rates are quite high. So that type of service is called IP trunking. Then you have more mobile cellular backhauling, which is the type of application that is normally provided in countries that have a lot of rural areas where the terrestrial infrastructure is very expensive. So, for example, in Africa or in some Southern American countries, and there the terrestrial base stations for mobile phones, they are then interconnected via satellite. And then this infrastructure is a bit more cost effective because there are many of those, and it's not a point-to-point connection, but it's more one gateway and a lot of base stations interconnecting with those gateways. And then we go into the area what was typically called VSAT applications, very small aperture terminal applications, and that's internet access type of antennas that you've probably seen already. Sometimes on gas stations you can see them, or even private homes can have satellite internet access. And today they are very cost effective. VSAT terminals available with relatively small antennas, and they can provide internet access. But normally the bit rates are relatively modest, but the process of improving. And since there are any questions? Since we're switching from applications from broadcast to internet access, many things are actually changing in the entire system, in the entire infrastructure that we're providing. And one of the key things that is changing is basically the coverage. So the satellite has advantages and disadvantages when it tries to position itself in a data communication chain. So it always has the unique advantage of being able to cover a huge area seamlessly, which all the other terrestrial operators always struggle with. So even in Germany, you don't have phone coverage everywhere. The satellite has this unique capability of just covering a huge area seamlessly. but the data rates are very limited, and the access to the satellite is a technological hurdle. So the new satellites that we're building for data communications, they are built differently. Instead of having a coverage like this, where you have a big area which is covered with a unique beam, and then the entire area receives the same signal, we subdivide the coverage into spot beams, and each of these spot beams is reusing the entire frequency, and by that we try to maximize the amount of capacity we can achieve with the satellite. And those categories of satellites are called high throughput satellites. I don't know, have you heard of that already in one of the previous lectures? No? Yeah. Oh, okay, then that's good. So it's basically, instead of building a coverage area like this, we make small cells, as small as possible, and each one of the cells can reuse the same, a maximum amount of frequency many times. And by that, the amount of capacity that can be provided by the satellite is much higher. And so there are already several generations of these satellites, these high throughput satellites that are currently being put in orbit, and the capacity is still increasing. So
other than the complexity, do you see any other disadvantage for spot beam satellites other than the ones that were being developed?
The complexity is a disadvantage, and I will address the other disadvantage, basically that the terrestrial infrastructure is also more complex with with spot beam satellites. But in fact, the demand really goes in the direction of more IP, internet type of access, and these applications that I was just mentioning. All of these applications I was mentioning earlier are growing in terms of demand. So while TV broadcast is questionable to which extent it still has a future on satellite, but all of the other applications I was mentioning, the demand is growing worldwide for that. And so the trend is really towards these type of satellites that have such a coverage. And the complexity is an issue. The other issue is the fact that if you have areas which have a concentrated demand and other areas which are rather empty, you cannot really reuse the capacity of other beams to compensate for that. So there's technical complexity that comes with it, and that's really one of the key disadvantages. So and within SES we operate geostationary satellites that have spot beams, but also MEO satellites. We're currently building this supposed to be mPOWER constellation, which is a really novel concept where these beams can be put anywhere on the Earth, a lot of flexibility, and then these services can then be combined. And then on the ground segment, when we build such a space segment, there will be another lecture where we actually go into more depth into how the satellite is actually built for a high throughput satellite, how the satellite looks like. That there is another lecture by Vani on payload, so that's why I will not go in detail on that, but I will talk about ground segments that are related to capacity. So I just wanted more market trend type of slide, but I think it's always interesting. You have the applications here, which I was mentioning on the previous slide, and you can actually see that they are really expected to grow, especially in the high throughput satellite domain. But I won't go more in detail. These are examples of high throughput satellites, of real ones. This one is called KASAT. It's by our competitor in Paris, Eutelsat. They had the first one in Europe. And then actually the first one that really had a significant amount of capacity is this one. It had more than 100 gigabit and already several years old, and that was Biosat-1. And you could see they designed the satellite to only cover the east and west coast, and they put the gateways in the middle. So the red dots are the gateways, and they covered here the coastal areas. That was Biosat-1. Okay. So SES, we also are following this trend. These in operation today, SES-15, SES-14 and SES-12. You could see that we cover well the Americas and Asia. We're in KU band. There are considerations for Africa and Europe, but there's more market consideration whether we want another satellite here. KU band is the band, the frequency. Have you talked about frequency bands already in another talk?
I mentioned a bit, but then there will be the next by Emma.
Okay. So KU band is the frequency band at 10 to 14 gigahertz. It is the frequency band that is traditionally used for TV broadcast. For example, the dishes you see here, the satellite dishes to receive satellite broadcast TV channels, that's normally KU band. That's the frequency band that has since the beginning of the 90s, end of the 80s, been used for satellite broadcast. And that is a well-used frequency band. A newer frequency band is Ka band. It's a higher frequency band. It's a higher frequency. There's also more capacity. The spot beams can be made smaller. So Ka band is better suited for data communications because spot beams can be made smaller. The satellites can have a higher capacity, but it's more susceptible to rain attenuation, Ka band. So it's more sensitive when it rains. So the signal is attenuated, and that's at the frequency band 20 gigahertz to 30 gigahertz. So you have a much higher frequency. The spot beams are smaller and has more capacity. So these satellites here, there's 12, 14, and 15, are all in KU band. And SES operates both, so we want to still continue to operate both. And in Ka band, we're planning SES-17 and OSUB MPOR. OSUB MPOR is a satellite that can cover the entire band here. Because it's in equatorial orbit, and then serve all of the customers in condition. So I just want to give an example, talk a little bit about the spacecraft, and then we go on the gateway architecture side. The satellites are really huge, the high throughput satellites, the geostationary satellites. In order to have such a big coverage here, like for example SES-12 covers all of these areas in many spot beams, and in order to achieve that, the satellites are really, really large. They have, this is one of the walls on the satellite, so you can see here the feeds that are radiating to the antenna, and these are the traveling wave tube amplifiers, and then you have here waveguides and filters, and these satellites are really packed with equipment, so they have over 90 amplifiers. An amplifier is the size of a microwave, so they have over 90 of those. Mm-hmm. And the entire satellite is the size of a truck. And it's really big, and a lot of waveguides, and it's a nightmare to test this, and that really pushes the limit of what analog satellites can actually do. And then in the other talk with Bhavani, we will be addressing new concepts of payloads to actually digitize more and make more of the processing on the satellite in digital, because to realize so many beams in analog is really a stretch, because it requires a lot of waveguides, a lot of filters, a lot of amplifiers. Each beam has its own feed in this on this satellite, so it's a significant amount of hardware. But we will go into the payload details somewhere else, but there's also an increasing complexity on the ground segment. Sorry.
Would you consider analog signal processing more robust in the harsh environment of space?
Analog signaling is more robust, yes. We have always been reluctant to go into processing in digital domain because of that, and also because the analog amplifiers are reliable and they're more efficient. The traveling wave tubes are more reliable, more efficient than alternatives, and the digital processing requires energy, and if you want to process a lot of data in space, it requires a lot of energy. And so actually avoiding to process in space and just using the scarce power in space to just amplify the signal has always been a good idea up to now. And it's only now that the trend in digital processing becomes such that it becomes more and more efficient. And it really, there are big improvements in digital processing that we're really considering to use digital processing in space. Because processing in space is expensive. You know, maybe on the ISS, for example, the laptops they use in the ISS are old laptops, because the electronics needs to be resilient to radiation, and if the electronics is performing and small, the transistors are small, they are more susceptible to errors, to upset events in space. Okay. So yeah, so digital processing in space is expensive, so that we will address that in another lecture. I wanted to talk about gateways. Gateway. This is BATSUF. We have using big antennas for TV broadcasting. This is Viasat gateway stations, and traditionally they've been big antennas, and the reason why they're big is because you want to avoid that this feeder link is a significant part of the link budget, that it becomes a limiting factor in your system. So you have big antennas, and we want to make sure that the connectivity between that part and the satellite is very safe and very resilient to rain and very reliable. And this has never been an issue in broadcast, because the satellite, this was a fraction only of the cost of the satellite, so that was never really an issue. But with high throughput satellites, and the type of processing you typically find in the gateways is a chain to transmit the signal and a chain to receive the signal. The transmission is then the broadcast signal or the link from the gateway to the terminals, and the reception is the link from the terminals to the gateway. So that is the typical processing you find in gateways, and normally the link budgets are such that they are very reliable. But in high throughput satellites, the problem is that we need to build many of those, because they support hundreds of gigabits, and you multiply the capacity in each of these user beams, then you also need to make sure that all of these user beams are connected somewhere. So if you multiply the user beams and you make a lot of small beams, and you multiply the capacity, somewhere this has to be connected to. And if the frequency bands for just one gateway is not enough, you need to multiply the gateways. And like, for example, in the Viasat example I was giving, the answer is that we need more than one gateway. For example, on SAS-17 we have 170 beams, and we need, if we use all of those beams, we need up to 16 gateways. So 16 gateways can be already very expensive. And so there is really a trend towards exploring new ways of building the gateways, because 16 times big antennas with all the redundancy and with all the complexity is a significant type of investment. So what is happening is that in traditional gateways you have a big antenna and you have fully redundant processing behind the antenna. And the new type of gateways, and HDS gateways, are considering smaller type of antennas, and only a fraction of the processing is done at the gateway itself, only the baseband processing, and then all of the backend processing and encapsulation and routing and data processing is done at a centralized location, so that we don't need to replicate this for all of the gateways. And only here we have the connection to the customer. So in the gateways we have a minimum amount of equipment, and the antennas are a bit smaller. And in the very new concept that I will explain now also, we also try to avoid that we have to have everything in redundant inside the gateways. So the gateways are expensive because the antenna infrastructure is expensive, all the mechanics make it expensive, and then the size of the antenna makes the beam very narrow, so you have to have a tracking system. They have to be precise tracking, so it's like a big telescope where they have to track on 2 axes, and all of this is expensive. These mechanics can be susceptible to outages. Yes?
It's fully redundant. You mean that everything is done several times again and again? Or?
Yes, fully redundant means that in this reception chain here, for example, I would not have only one amplifier but two, and you have a switch. You switch between the two. If one fails, you take the second one. I don't have one frequency converter, but two. Or I have several, and then at least one which is there just in case one fails.
So it's like spare parts.
Just a spare parts. Yes, everything in the chain is built up in a redundant manner, and that basically means that you that you actually calculate the availability of this link, and you calculate what is the probability that this entire system breaks down. And it is often a combination of all the probabilities that all of the subsystems break down. And normally if you multiply all of the probabilities, at the end, the probability that the entire station breaks down is really not negligible. And if that breaks down, your link is gone, and you cannot guarantee your customer service anymore. So the traditional solution for that is that everything has a spare part ready to take over in case it fails. So for example, the amplifier, we always have a second amplifier just standing there ready, normally even powered on, in case that one fails, and then if it fails, there's an automatic switch. We have the same here, the same here, the same here. Normally the entire chain is completely redundant, so that the availability of the entire gateway is 99.5%. And only that you can guarantee. And if you have to multiply that by a large number of gateways, it makes it really, really expensive. So there are new ways of exploring to build the gateway networks, which I'm going to try to explain now here. So the first step here really is that we split this. Instead of putting everything in one gateway and just replicating this one gateway, there is already a split in the processing. Here the link is normally then just, the receivers and transmitters are still part of the baseband processing, so the modulator and demodulator are still part of this here. And then here we have baseband frames over IP, that's basically just the digital signal, but in a very raw format, in the sense that here we have constant rates always, and here the internet traffic can be statistical traffic. So the backend processing is encapsulation, scheduling, and routers. There's a big router here, and then the customer is connected here. The customers, they come and then where do I connect? And here, there's an edge router. And then we do all of this, and then we would still have the problem of the redundancy in this architecture. There is still, this problem is not gone, but in order to make this problem go away, there is one concept that we're currently exploring and building up that's called smart gateway diversity, or smart gateways. And it was actually ESA who came up with this some time ago, and they presented this as a type of study, and it's not. It was explored and studied more in details, but up to today there's no network yet with this concept. So we're I think a bit trying to make this novel. Let me just try to explain how this works. So in this smart gateway diversity concept, we have still redundancy, but organized in a different manner. So instead of having redundancy in all of the gateways, we have redundancy. Each gateway helps each other out. That's the type of idea. Instead of that, each gateway is on its own and needs to organize redundancy on its own. So it's in fact the principle of an insurance, that you're a big community, and the probability that you all have a problem is small. So that's the principle of an insurance. It's the same here. We have a gateway network. Here it's 3, but for example, VASA 17 is 16. So you can imagine that the ratio is already more favorable. And then if it rains, we can, this gateway is gone, we can reroute the traffic, and then we establish the route here, and then this gateway has backed up that gateway. That is the concept, and that requires that we are able to switch that traffic here and to make this rerouting, and that requires this possibility to reorganize the traffic, which is something we're currently developing.
Sir?
Yes.
You said that the gateways have to work together, but then it's not true redundancy.
Yes, so in this scheme, the redundancy is in the network in the sense that, for example, this gateway, you can imagine it has only one transmit and one receive channel. So the availability of that single gateway might be, I don't know, maybe just 80%, 85%, because if you multiply all of the probabilities of failure, there is a fair chance that it fails because there's no redundancy in it. The second one as well, and the third one as well, up to as many gateways as you have. But the redundancy lies in the fact that they can back each other up. For example, number 3 now took over the traffic of number 2. So number 3 was the redundancy.
Doesn't that reduce processing capabilities?
Sorry?
Doesn't that reduce processing capabilities?
Processing capabilities we need still redundancy. We need still to have the redundancy provided in the form of gateway 3, but this scheme allows us to operate redundancy in n to n plus p type of manner. So, for example, in this specific example, it's the ratio of redundant equipment to operational equipment is 1 to 2, and it's not 1 to 1. And if we have 16 gateways, we could have one spare. Then it's 1 to 16, and it's actually. Sorry, you want to ask a question?
So the drop of gateway 2 would be only given to one of the other gateways, or would it be split up?
Yes, that's a good question. But in the first scheme, n to n plus p, so n would be in this example n would be 2 and p would be 1. So it would then be this particular example. But if we have more gateways, the ratio is more favorable, and in this particular case, we have a hard switch of all the capacity here to here. But you're right. You could actually imagine a situation where all of this capacity that has broken down, and we need to find another way. It could be split up to gateway 1 to 1, 3, 4, up to 16, and that is actually an even more efficient way, but it is more complex because you need to split. In this case, it's just switching from this gateway beam to that gateway beam. It's simpler. If you would need to split up the traffic, it's more complicated.
So no gateway can be used for 100% because otherwise it cannot take over the task.
In this scheme, we still need to have redundancy, yes. But in this setup, so if you imagine that we have 16 and then we have one redundant, we only need one redundant, or maybe 2 out of 16, instead of having 16 times 2 type of equipment. So it's still an advantage. And the question you were asking is fully correct. It would even be better if we could split up the traffic and distribute it to all of the gateways that have spare capacity. And that would even be better, but it's more complicated.
Yeah.
I have two questions. So in today's world, do our gateway is being used as like 100% utilization, or do we keep buffer in gateways usually, like in the industry? If the beams, they can be pretty close to 100% utilization, so that there will be limitations in the amount of traffic. Normally, the limitation that is first hit or that is first experienced is the forward link. So that's basically the uplink. So people who use data services, they often download a lot, or they request a lot of data, and so normally this what we call the forward link, the link from the gateways to the user beams, is normally congested first, and that's normally where the data, the link is normally fully utilized. My second question would be like, so you said that this is not existing today, right? This concept.
No, but we're working on it for FASA 17.
What's the challenge that has stopped us from accepting this or doing this?
But the first generation, well, first of all, it's a problem specific for high throughput satellites. So in traditional broadcast, the problem does not really exist in this. Why it was never so much of a problem. So this problem that the gateways actually needed a new redundancy concept only came with high-throughput satellites, and that's only since 10 years or so. And then the first generation of high-throughput satellites, they were very relatively simple. And one gateway was connected in a fixed manner to a certain cluster of user beams. And then if you wanted to activate that cluster of user beams, you had to make sure that that gateway is present. So you have your coverage there. If you go back to one of the slides, you have here, maybe this is a good slide, I don't know. So you have here a network of gateways. So one of these is connected to several user beams, and that one is connected to several user beams, and that one is connected to several user beams, and so on. So the first generation of high-throughput satellites was relatively rudimentary. And in order to make the switching work, you need also a switch on the satellite. And you need an intelligence to actually detect the failure and make the switch. And that is only something that is technology that we are introducing with ISS-17, and I think other companies are working on similar things probably also. But, and it's not a secret. I mean, yes, ESA has published it. So and yeah. So because here you need the switching capability. This link needs to be switched on the satellite to another feed to that link, and we need to actually detect the range fade and activate the switch. Yes.
Maybe I have a question, because according to these gateways, they are prepared to use normal communication ground base, or they are prepared special. You are going to prepare special high performance like optic fiber solution for this.
You mean connecting the?
Yeah, between gateways there is no.
You mean this link here?
Yeah, exactly.
This link is a fiber, but it doesn't have to be a dark fiber. So it's because here the modulator and demodulator are here, and then well, here we still have the down converter, modulator, demodulator, and then at the output of the demodulator we have baseband frames over IP, and normally they just need very high reliable data rates, so we can use one of the standard fiber products, which is STM something, so the typical fiber products, and it doesn't need to be a dark fiber, which is also good because that makes this not so expensive. So. But it needs to be a fiber connection, it needs to be a very reliable link. It's very reliable. Okay, is there any other questions? So I think this is very good. This is actually going, these slides were intended to go in this discussion we just had, so I'll just skip over them. And if you have any further questions on gateways, you can actually, then contact me also later. So today we're working on these smart gateways, so to make the gateway network more efficient for high-throughput satellites. So that is already under development. So what comes next? What is next in the gateway pipeline? There are new frequency bands, and again, ESA is working on those, and that's really exciting. They are called QV bands. They are at 40 gigahertz formally between 37 and 60 gigahertz, and the portion allocated to satellite is 5 gigahertz. So it's a lot of bandwidth. So it's in Ka band we have 2.5 gigahertz, and so this is a lot of additional bandwidth that we could use, and but it also has a problem. This is even more susceptible to rain, this QV band. So if it rains a little bit, this link is gone already. So it's a problem. That's why actually this is a natural evolution of the smart gateway, because if you are very susceptible to rain, this QV band only works well if you have smart gateways working. If you cannot switch between gateways, you can never make this reliable. So it's a logical evolution, and with this we can really increase the capacity of the gateway. And so that's very exciting. ESA is working on QV band. Then there are companies that are working on optical feeder links. There are companies in Germany, Switzerland that are working on optical feeder links. Also, ESA is working on optical feeder links. We haven't yet seen. In fact, I think it's technically super interesting, but we haven't seen yet a convincing breakthrough in terms of capacity that would bring the optical feeder links. So I think optics, they have these advantages that can be for quantum key distribution, there can be advantages using optical properties. But the feeder links, we actually need something that has a lot of capacity. And the optical links, it's still a question, but there's some work going on there. So I want to spend the rest of the lecture a bit more on the other side, on the terminal side, terminal overview side of things. So if we go away from the gateways, and what is actually on the other side? So on the other side we have terminals. I mentioned earlier on, you have these typical small terminals that are already very cost effective today. They are often used, and the capacity increases a lot with the high throughput satellites for these terminals. So you could have, and they are very cost effective. They can be a few hundred euros with the antenna, and then you have a satellite connectivity. And especially in developing countries, it's attractive for villages. Villages that are poor, normally they can still afford this for the entire village. You can have internet, so that's nice. Then on the more expensive side, the terminals today. This is a company in the UK we're working with, Isotropic. They're building antennas, phased array antennas with new technology with lenses on top of the phased array. To point the beam, to steer the beam, and these can be used on for mobile applications and for mobile terminals. So on the terminal side, there's a big tendency on the antennas to phased array, electronically steered antenna systems, and that is one of the key technology drives. I wanted to go a bit in the technology overview of how the link between the terminal and the gateway is working. Have you heard already about these standards in our lecture? No, not yet. So I will explain the principle, and then basically we can go into as much detail as you like later. So the problem, we have a gateway. We want to interconnect all of these terminals here to the gateway. So it's working as an access system. We have one big pipe in this direction where all of the traffic needs to be put for all of these users in the user beam. And on the return link, they all need to transmit in such a way that they don't interfere with each other, and that they can share the capacity. So there's basically the problem that the resources need to be shared, and that they avoid that they interfere with each other. So if this guy transmits on one frequency, he cannot transmit at the same time as another guy on the same frequency. So there needs to be a strategy, a sharing strategy. And this is defined, this sharing strategy is defined in these standards. And this big pipe here, the blue one, is defined in this standard, DVB satellite. That was the satellite standard, satellite 2. And then recently there has been an extension to that standard. And this is called for return channel systems. And that's also the second standard. DVB is a standardization body. And most of the transmission technologies are based on these standards. So these standards are really very widely used for these links, so for that return. So this one specifies the blue link, and this standard specifies the return. They're actually freely accessible. You can find them on the internet. So I can provide you some information. I just want to give an overview. So on the forward link, DVB-S2, it looks like a big carrier. You have a big carrier that occupies a certain frequency, and on the return link, all of the terminals need to be given a certain frequency slot, normally much smaller. Then it can be a single channel per carrier, or they can be divided into smaller slots where they share the capacity. then the transmission actually one of the key technology developments which really helped data communication on satellite after broadcast was a technology that is standardized inside of the standard. It's called adaptive coding and modulation, and this is part of the DVB-S2 standard. And it's one of the key advantages that make data communication really become economically viable. And the reason for that is that the links don't need to be planned for the worst case. The broadcast links are normally planned for the worst case. You take the worst possible antenna and the worst possible location, and then you add rain fade, and then you add some margin, and then you plan your link that it still works under the worst possible conditions. This is normally never the case, and there was no technology that would allow the links to adapt to rain fade, to sunny conditions or to very bad conditions. So if the link is very attenuated, you had to plan for the worst possible condition. So it's a bit comparable as if you would have a big motorway and you would run on 30 on the big motorway. But maybe some part down the road there is a bad country road, so you need to run at 30 because somewhere down the road there's a country road. And you cannot profit from the fact that 90% of the time you have much better conditions. So this technology allows the conditions to adapt, and they can only adapt by the fact that you can actually measure each terminal link condition is measured and it's sent back, and then the gateway, the modulators in the gateway, they change the efficiency of, and this, by efficiency we mean speed, the speed at which we transmit. For each individual terminal, they are adapted. That's why it's adaptive coding and modulation. And so when you have sunny conditions and when the terminal is, has a very good SNO, you can speed up. So it's like on the motorway, you don't run at 30, but you run at 120. And then when you come to the country road, you brake down, you go slower. So then when you come to the country road, you switch to another gear, and then you continue to transmit. And that only works if you can actually measure the link quality at the receiver, and for that you need to return pass. And so this entire mechanism is adaptive coding and modulation. And it's only with this that data communication over satellite really became commercially viable, because before that it was really not. So this is key. And today it works really well, adaptive coding and modulation. So the systems today, they really work. The encapsulation, maybe for the sake of time I don't go too much into details of this. We want to transmit IP datagrams, which can be a different length, and the transmission over the satellite, they always have a fixed length code, so there is a problem of fitting a variable length IP datagram on a fixed length encoded transmission train. This is like a train. You have fixed length wagons on a train, and you need to put variable length datagrams on top of that. And there's a standard encapsulation standard foreseen for that. It's GSE. On the return link, the access scheme where we saw all of the terminals they need to transmit and organize their transmission so that they don't interfere with each other. And there is a big fundamental technology used by almost all the systems called MFTMA, multi-frequency time division multiple access, and it basically subdivides the frequency into slots and time slots, and each of the terminals gets opportunities to transmit its information. It's like containers where the terminals can put their capacity and then they transmit. And if they do that on this grid, then basically they don't interfere with each other. So it's an organization of it's the way the information is organized on the return pass. Okay. How much time do you have? So 5 minutes or?
Yeah, 5 minutes, yeah.
You have 5 minutes?
Yeah.
Okay.
No, I was discussing before the video.
Okay. Good. The modulation, I don't want to go into more details on that. Maybe it's for the sake of time, and it's part of the standard. Then all of these services, they are organized into service classes. So then you have this mix of different terminals. And today we operate networks of different customers. You have consumer customers, these small terminals that I was showing earlier on, consumer, and they are mixed with customers on the same capacity with backhauling customers, and all of these customers are mixed, but they cannot really have all be treated the same. So there is a sense of service classes that is implemented, and this is these different classes. They are defined as a service level agreement. How much committed rate and peak rate each one of these services can actually use for for example, the backhauling customer gets a certain service class, the internet access customers has another service class, and if the internet customer is congested, then he should not squeeze out the backhauling customer and so on. So there is a hierarchy in how the services are organized, and these service classes. They are normally defined in terms of committed information rate and peak information rate, and then you have certain service pools, so real-time pools and critical data pools and best effort pools. Normally, normally in practice there are always normally three classes defined: real-time, critical data, and best effort. There's rarely anything else than that. And then you have certain capacity pools, and then, for example, all of the backhauling would be organized together, and that would then avoid that, for example, if the broadband, if the internet access part of the network is congested because people come home and they start to browse on the internet and watch a lot of YouTube, then they don't steal the capacity from the others. Okay, so that's. On satellite, in these terminals, there is actually also the need to work on higher layers, so on TCP and on HTTP. So the systems today, they have technologies implemented which is called TCP acceleration and HTTP prefetching to avoid that, because the forward link, the most expensive part of this data communication link is the link from the gateway to the terminal, this forward link, and you don't want it to be wasted with any capacity which is really not used. So first, the voice calls, the headers of the voice calls, there is a technology that is used which is called header compression, which over satellite avoids that we repeat the same voice headers, because the voice over IP communications, they use very small packets and they always repeat the header, and normally it's not a problem because on terrestrial links it's not such a big issue. But over satellite we can reduce that, and there's a few percentage gain. HTTP prefetching allows us to speed up the browsing, and the content can be compressed, so the content is compressed. So if you browse over the internet over satellite, the pages they build up after a few seconds in once. This is prefetching. And then the TCP protocol, I don't know if you're familiar with it, but it's a protocol that actually avoids congestion. It slowly builds up, so it sends something, then you get an acknowledgement, sends getting an acknowledgement. And the problem with satellite is that because of the delay, it makes it slower. So TCP over satellite is slow because of the delay, because it has a tendency to ramp up, and TCP is used a lot, so whenever you browse the web, you use TCP all the time, hundreds of TCP sessions. And so the delay of the geo satellite is a problem, and in order to avoid that, there is TCP acceleration that cuts the TCP on a satellite modem. The TCP connections are cut in the modem, and they are replicated on the gateway side. So when you request a web page, I don't know, CNN.com, the modem records that, and it just informs the other side, I want this page. then it gets it, and then it transmits it with a compressed proprietary protocol, and then the page is built up from the modem. So if you browse, it takes a little bit, and then everything comes at once. So that these technologies are highly. The receiver processing inside of the modem comprises different stages. So we have synchronization, demodulation, timing recovery, symbol recovery, and yeah, I don't. Well, then up to the MPEG frame, which is demodulated and standby. The coding that is currently being used on the latest standards is very effective for it. It's the same family of codes that's actually used in 5G LPC codes. Okay, so I don't want to go into more details for the sake of time, but. Yeah, so the innovation today on satellite communications, the innovations on the terminal side, they are really, really important for us because they will determine where we can actually site capacity and what will happen in the future. So we're absolutely interested in working with these companies. There's a lot of innovation going on the antenna side. The satellite has the problem that the access to the satellite is always the problem, and the antenna is always the problem. And electronically steerable antennas are currently being developed with different technologies. Kymeta, for example, they use they are in the market since recently, and they use a technology to avoid to have to use too many active elements. Then there's a company in the UK. It's called Phaser. They have another technology for electronically steerable antennas. I was mentioning earlier on the company Isotropic who we're working with, and they want to reduce the number of active elements by putting a lens on each of the elements so that you need less active elements. They're less expensive then. But these electronically steerable antennas are really important, and if they are cheap and performing, and so it's good for the entire industry, and the access to the satellite capacity is always a kind of hurdle that is important for us. I don't know if you've taken the airplane recently, but you see more and more on the big airplanes that they have these satellite antennas on top, and you have Wi-Fi on the airplanes. So that's a big market that's currently being developed. Also cruise ships. And then there are trials with cars to put satellite antennas on cars, to have TV in cars and so on. But that only works if these antennas are really successful. So the innovation on the antenna side is really, I think, the most important development right now, and will determine where satellite technology is going to be successful in the future. Yes, so I think really the next steps after this next generation high throughput satellites are the next challenges for us are really working on QV band, as I mentioned earlier on. And in the talk by Galvani, where I will also intervene, we will talk about payloads and dynamically reconfigurable payloads. These are things we're currently working on. Reducing the cost per bit and the capacity, improving the capacity of the satellite is always a driver. And integrating the satellite network with 5G networks is also an important development for us. And for that we need to adapt to the 5G technologies for virtualization of their links and the type of link layer technology they are using and so on. So these are really the areas we're focusing on right now. Okay, so I don't want to take because the leaders to have this. Okay, was I too much time?
Oh, it's okay because the last part will be shorter. I promise.
Okay, so do you have any other questions before the break? Okay, we will see each other again. So if you have a question, then you ask me.
I have one question about that presentation. We don't have it in Moodle, but
Yeah, I
could
will
you
show you
please
that.
share it with us?
Yeah,
Okay.
You will get it.
I will integrate everything today. My part in this part, and by tomorrow should be there.
Okay, perfect.
Yes.
Thank you.
Okay, thank you.
Thank you. Thank you.
All right. So, just one thing. So you said that because normally it's until 4:30. Maybe I take 10 minutes more if you don't mind, and we will complete it with the integration part. Okay. For me, it's fine. Yeah, okay, because the last part is and only was 45 minutes, but I also took more time in the process.
No, me not. But I don't. Right now. Right now.
Oh, it's okay. No, I don't want